one of the students, but yeah, could have done that.
We will start in a second. Oh,
Are we losing connection or what?
No.
I can see John, right? Is it John?
Yes, and you can even make that he will see everyone. Okay, now they likely see.
Okay, can they hear us? Hi,
Yes,
Levi.
we
Hi,
can hear
Brayden.
you.
Brayden? Is it Brayden?
So dark in there.
Yeah,
Yes.
it looks like you are so dark there.
Get lights off.
Is it? They really don't like us having the lights off. Here, just turn it up a bit.
Probably don't hear us.
What was happening when
I
Can they
think
hear us?
maybe. Yeah, we can hear you. Oh no,
Can you
I guess
tell
we have to
something?
turn it on and off.
They speak between each other, but we don't hear them.
Just talking crap.
No, we hear you. Can you not hear us?
Brayden, Levi, can you tell something?
Hello?
When I
No?
was up there, I had to put them on the projector.
I can hear
and
him
then for some
talking.
reason the sound would come through.
Okay, well, it is more important to have projector than a projector.
But we can just
let's
say
try
hi.
it as an experiment.
So when last
Try to
meeting-
say something right now.
You can hear us last meeting.
Hello?
Oh yeah.
Oh,
Good.
okay, good. What about John? We still can hear him. John, can you hear us?
I can. Can you not hear me?
Oh, yeah.
Now we can.
Perfect.
But during the presentation, probably we will not be able. How would you? I ask questions then.
Is Javed there?
He
He
should
will come
be.
later because he's still working
He
on a
should be.
photon. Or on
Oh.
the photon or whatever he's working on.
Oh, there he is. If we have questions, I'll just message Javed on Slack.
And then we can, after completing the presentation, we can go back to interactive mode and you will speak freely.
Wait, you and Javed have a Slack?
Does it sound reasonable?
We're inviting you.
Overcomplicated is what it sounds like.
Come on. You're not in the Kalina group anymore.
There is the button share content did disappear from the setup.
Well, Sergey happens to be paying me. I'm still working. You should add me to that. Most of it's just photon admin stuff. I'm not working with you, I've been emailing Javed.
So what are we going to do is there will be another set of meetings on Friday, and the schedule will be distributed soon. And on Tuesdays we'll devote time more to the research update and the code development. So today's presenter will be Dr. Fatima, and she will share her experience in including dependence on momentum into the codes for electron dynamics. For the next meeting, we will need volunteers sign up for quick overview of the protocols, computational protocols to do electron dynamics. And we can do it by email in private mode, but just letting you know that such opportunity will be available. So the speaker is invited to the stage. So let me do a brief introduction. There are several members of this, of two groups and bigger group who are either practicing or actively doing electronic excited state dynamics, and there are different varieties of codes. One big stream is based on so-called surface hopping, another is based on the density metrics approach, but when we look on the direction from molecules, from confined nanostructures to larger periodic solids, their electronic structure explicitly include dependence on momentum, and this feature is included into codes for electronic structure units, but is not included in electron dynamics units. So there is an attempt and effort to make dynamics in systems where dependence on electronic momentum is explicitly needed. And Dr. Fatima is doing some efforts in this direction. What is yours?
So I'm going to present today about the methodology for Q-point resolve dynamics in silicon nanowires in three different growth directions. In our previous study, we studied optical properties, electronic structure, and electron dynamics on these same three nanowires, but it was momentum conserved.
Go to presentation modes that it will be bigger. Yep.
We are stick with the same number of K points this time also, but in our previous study, electron transfer from one K point to the same K point, we didn't include the electron transfer from one K point to another one. So now, today I'm going to present where I included the electron transfer from one K point to another K point. Here is the band structure for three different silicon nanowire grown in three different directions: 100, 111, and 211. For a silicon nanowire grown in 100 and 11 direction, we considered 4 K points, and in silicon nanowire grown in 211 direction, we considered 3 K points. So this is a kind of a complicated process. So electron can transfer K point 1 to 1, 2, 3, 4, and 2 to 1, 2, 3, 4, and like this, and in the reverse way, like 2 to 1 and 1 to 2, like this. So
can you interrupt and ask?
Sure.
Can you go back one slide and illustrate this 1 to 2, 2 to 1, what you're talking, just go to the board and show or select it with mouse. What do you mean 1 to 2?
So key point for these 2 nanowires, we consider key point 1. I mean key point 1 to 1, key point 2. So here key point 1 is point 1. And key point for these 2 nanowires, and key point 2 is 0.16, and key point 3 is point 3 something, and key point 4 is 0.5.
Jared, you had a question?
Yeah, I'm just wondering, so you consider the 4 cap ones, right?
Yeah, for these 2 nanowires.
So how we decided that how many cap ones you need to get a reasonable result?
From this band structure, we decided it should be more than 2 cap points, 3 or 4.
But why not 6?
Maybe 6 is good.
So how, I think the question is
Yeah,
how
I
we know
mean,
that 4 is enough.
How we decided how many cap ones should I calculate? Or
I think it's on the banding. It depends on the banding of these states, like here.
I would say the larger number, the better. But
Yeah.
I mean,
But
I would
again-
say reasonable. What's the reasonable one should be?
To prove it, you probably need to go beyond 4K points and then show that your band structure is not affected very much if you go to 5 or 6K points.
how many key points are in these pictures?
4 for these 2 nanowires.
It looks like more finer.
Oh yeah, it's just scale, but we considered 4K points for
So,
the
it
calculation.
is like spline connection between points. It looks very continuous.
Yeah. So,
This one looks like maybe 8. No?
It is just scale. Like I denoted x-axis.
No, not the numbers, but the lines themselves look very smooth.
These lines?
Yes. If it would be 4K points, it will be like broken line with sharp
two
angle.
on
No?
4 points.
Okay, well, let's try with 4 and plan to check if it
But
converges.
this is not very hard to calculate, right? You can go to like add another 2 points here, right, and see how this change your
I-
structure.
Mm,
Because technically, you don't need to calculate all 6 or 8K points together, right? You don't need to run the job with 8K points. You can run the job, like you have already your 4K points, now you can run another job, adding another 4K points, really by hand, so they will not overlap with the same symmetry, or whatever, with the same names of these K points which you use here, right? So it means you just run another calculation with 4K points, but these 4K points, just choose them to be different from those which you are having here. And then you can add this information in one plot, and then you will have 8 points. And then comparing your 4 and 8, or 4, 4 and 8, actually now you will have set of 3, you clearly will see whether this additional 4 make any difference, because they might really just lie along these lines and showing no really any additional features to your band structure, right?
So you mean the band structure only for more?
Well, yeah, the band structure with additional 4K points, which will be not the same as these ones, right?
Yeah, it's easy to calculate the band structure for more K points, but it is hard to consider more than 4K points for further.
No, I understand, but still, like, would be the hope is that adding this additional 4 points, not really changing qualitatively, not changing your trends. You will not see significant decrease in your gaps. You will not see any special features in your band structure, right? If this is not happening, then you are safe to say, well, we clearly see that 4 points enough.
Oh, okay.
It just would be a proof
Okay, I see.
to
So,
say that whatever you do later on, 4 is enough.
you mean for justification of number of K points? Okay.
Kind of to answer exactly the
Yeah,
question
that's
for
that's a
general.
kind of cap one sampling, but my actually confusion about when you're calculating the transferring from the one cap point to other cap points, in that case, how many cap points we need to consider to calculate, I mean, how many transfer from one cap point to other do we need to calculate to get an overall reasonable result?
Can you go one slide forward?
More?
No. Yeah.
Oh,
Yeah. So what are coupling files? The slides here look very jammed, and it's like 20 slides are skipped. So what are coupling files? What are their structure, and how expensive is to calculate them?
here it is. This is.
But just define, what do you call coupling files?
Here coupling files, there are two kinds of coupling files here. One for coupling dot k point, suppose k point 1. And this is the number of.
But this is
Coupling.
coupling
In
for
the- in
what?
the
What's
table-
the physical meaning of these couplings? Couplings of what?
One,
Spin
orbital.
orbit couplings
Yeah.
or what? Non-diabetic couplings, electron hole couplings. There are many types of couplings.
Non-adiabatic coupling.
Non-diabetic couplings, okay.
We consider that.
How are they computed?
So one k point to
No,
one
no,
orbital to another orbital.
Yes, but how many of these couplings files you need to generate? Is it just for each
So
k point
number-
is one file, or it is like a long trajectory? How long is trajectory?
Ln trajectory.
Huh?
Ln trajectory. So it's number of orbitals times number of orbitals.
Well, one coupling file is like matrix, depending on number of orbitals. But how many coupling files? What are the XXX in your notation here?
This is from 1 to around 800.
Okay,
At XX for k point for a particular k point.
okay. For particular k point,
Yeah,
it is
suppose from-
several hundred coupling files.
Exactly. So k point 1 to k point 1, it's around 7 or 800. For and second kind of here.
Escape, maybe escape on the keyboard.
Yeah. So here, this is k point. Suppose this is k point 1 to k point 2, or k point 2 to 1, or 1 to 3, 1 to 4, kind of like. So and for each, suppose k point 1 to k point 2, it has like another couple of hundred k points.
So what is the conclusion and what is the answer to Jabit?
I
The
still think it's not really what he's asking.
No. There is an indirect answer. The non-adiabatic couplings along trajectories are expensive, and if you ramp up number of k points, this calculation will be even more expensive. Therefore, one cannot be too ambitious, at least at the first attempt. And
Yeah, that's my question. What
Okay.
is the reasonable one here? I mean,
it will have no sense to go below 4.
okay.
But the larger.
But again, if your
the-
density of state is not affected by the increase and further increase in the k points, this would be justification that 4 is good enough. Because quantitatively, nothing is changing with your electronic structure if you go beyond whatever number of k points.
In this sense, applying this code to a confined quantum dot will be ideal. It will converge even without k points, with gamma point.
Of course.
Um,
But in your case, you have only specific, you have only one, like you have a rod, right? Is it a rod? Is it one-dimensional
Nanowire.
or two-dimensional? Huh?
Nanowire, one-dimensional.
One-dimensional. So means you really just consider, like you have confinement in all two directions. It's only one direction where you have to care about k points, right? And again, you're probably not expecting that. You still, again, the idea is that if the size of your cell is big enough, you don't need a lot of k points, right? So it's really kind of how say trick you make. You choose very small X space cell, then you need a lot of k points to be accurate with your electronic structure. or backward. You can use huge cell along this x direction, of course, right? You can use, I don't know how many, 3, 5, 10 nano whatever ensembles together along this direction, and then the size is really big enough so you don't need a lot of key points. So you always can play with size in x versus number of key points, and I think you just really need to show that because your cell is big enough, 4 key points is good enough, qualitatively nothing is changing, right? There of course might be some small things due to the really accuracy in the specific values, but qualitatively nothing is changing, and then you are safe to use your key points.
Can you tell that most of the bands have parabolic structure, and 4 points is enough to represent parabola? Actually, even 2 points up. Can you go back to your dispersion curves?
Yeah, if it's parabolic, you probably need only 3 points.
So most of these bands are parabolic, at least homos and lumos. If one go further, there is a crossing of the bands. Well, for parabolic 4 is definitely sufficient. For those that cross, maybe one may wish to have more.
If parabola curvature is much higher, then do you need more number of K points?
It will, if you ramp up number of K points, it will, final results will converge very quickly. So if you like try 4, 6, like 8, 16, then it stop changing. It will stop changing. Can we go one slide forward on the 1? Let me answer one of the questions that was skipped here. So, what are coupling files? One does the trajectory of all ions, which is long. A long time, you have all positions a long time, they are changing randomly. And then one does have the orbitals, which do have index of orbital and index corresponding to value of the momentum, right, at each point of time. And then one has another set of orbitals at time t plus delta t at different index with different k point. And then one can find their overlap, multiply by some constant, and take that it is coupling that has 4 indices: initial band, final band, initial k point, final k point. And all these couplings do depend on time. So the time goes discrete between about 1 to 1,000 steps. Okay, so you wanted to tell it, right?
But I think there are, okay, how many people here who really have no ideas what we call non-diabetic couplings?
Non-diabetic coupling.
Okay, and what about, do they hear us or not?
They do not hear us. They hear us, but we do not hear them.
Okay, so what about Braden? No problems with non-diabetic couplings? Means you do need some explanation.
He understands.
So then I guess probably, I don't know, Fatima, can you give some, without formulas, maybe just brief idea of what exactly we call this non-diabetic couplings? What is it?
So
And why do we need it? Why do we care?
it's something related to heat.
Keep going.
You're not answering, it's not exam. You're not answering our questions. You are
There are several
explaining
group
it
members
to,
who are
to students.
hearing for the first time. You are like a teacher. So explain.
So in order to calculate the molecular dynamics, we heat the molecule,
Okay.
right? And then adiabatic means the heat cannot go in and out. So non-diabetic, we can lose the heat maybe in the system.
Okay, lose the heat from the system. So you mean?
But where do you lose it? What is the
The
mechanism of losing the heat? Where
Recombination.
energy is not disappearing, right? It just goes from one type of energy to another. So where
Yeah.
does it go?
recombination, radiative,
Non-radiative.
non-radiative.
But again, it means nothing.
Explain it to more broader general audience.
What exactly happening with your molecule when you say you're heating it?
Yeah, so electron goes from lower energy state to higher energy state. Electron
What
gets-
energy usually you need to use? Like what would be the values to use heat to go from one electronic state to another electronic state in molecules?
For heat, it's phonon.
Huh? Okay. So you have actually two types of carriers here. One is it's photoexcited state first, right? You
Photon
you
and
go
phonon.
over the gap, which is pretty significant. It's several electron volts typically, right? And if you convert it to the heat, it's a huge, like your temperature should be higher than temperature of sun, right? So which is something around anyone remembers?
5,000.
5,000 kelvins, right? So that's why, of course, you cannot overcome this through the heating. You use light, right? So energy of light is enough to kind of put your electron to the unoccupied state. But then, neither of the system would like to be in this excited state, right? It should go down to the ground state. And there are two ways how it can go down. Either radiatively, so as much light was absorbed, as much it can release, right? But this is really very, not very common way. Depends on the molecule. The other way, it just gives a little bit and a little bit and a little bit of its energy to the phonons through the interaction with the phonons, with the vibrations of the lattice. She's talking about solid state, or just vibrational motion of nucleus in a molecules, right? So the energy of nuclear is of course much smaller compared to this energy splitting in the electronic levels. So that's why it cannot give all 3 electron volts at once to the phonons, because phonons probably millions times small energy require. So that's why it goes step by step, just giving it by a little bit, a little bit, a little bit. And this also, giving it a little bit, it goes not directly back to the ground state, but a little bit in its excited state, right? Because again, in a solid state we have a band. It's many, many states, which are not really discrete as in molecules. It's kind of a band, right? So going step by step from one electronic level to another electronic level. And this energy is released to the phonon. So in other words, you lose in your sun energy, if you're thinking that it's absorbing sun energy, to the just vibrations, to the heat. Or you can think you can use electromagnetic field, and again, this energy of the field is lost to the vibration motion, right? Or phonons, or vibrations, which means you're heating it, right? So now, these processes is possible only if you include the coupling between electrons and phonons, or vibrations. But usually, it's much simpler to solve it without these couplings. You just say, well, we just consider electronic degrees of freedom, we don't care about atoms, because they move much more slowly, right? And this is true, but then you cannot really include these processes of releasing this energy to phonons. So for your non-diabetic couplings, you can imagine that if you don't include interaction with phonons, then wherever you excite the electron, it will be moving along its excited state, right? And excited state is also having this parabolic or whatever shape, and it's kind of, but it's never really jumped to another electronic level. It just stays in this state forever. And this is what typically happens for the adiabatic dynamics. So adiabatic dynamics will allow to go along the excited state, but not jumping between different excited state, electronic excited state, right? So this jump from one electronic to another electronic level requires the coupling with phonons. And this is what we call non-adiabatic coupling. And there are some formulas which Dmitry were trying to write for this coupling, kind of thinking that you have electronic wave function on the left and right, which is changing with time, right? T and at moment T and moment delta T. And kind of overlapping these two wave functions will give you, because again, change in a motion with time of this electronic wave function if it feels nuclear, will be kind of really, this change is due to this interaction with nuclear, right? And that's why it's kind of dig inside this formula for the coupling respondence. So in other words, non-diabetic couplings in this case have a meaning of the coupling between electron degrees of freedom and vibrational or formal degrees of freedom. And this is a mechanism for kind of going from the very excited state, when you're excited probably not to the homoluma, but really much higher energy, right? And then after, I guess probably picosecond range, right? All this excitation will be lost to the phonon motion. You're just heating the system, right? And then when it's kind of trapped in your homoluma, when it's going to the bent edge, right? Where you have really big splitting, then again, it either releases the light, if this is possible, or it goes through the multi-phonon processes, which is much slower, non-radiative, and so on. It's much more complicated mechanism.
You agree? Right?
Yeah.
And thank you for
But now,
just
complication-
a second before we go forward. Here is the summary of what was the discussion.
Coming in the camera.
no,
No.
they can't see it, I guess.
Okay, they cannot see. But next time presenting on this subject, maybe these points need to be covered. So dissipation of energy from electronic degrees of freedom into thermal motion of ions, right? So we all agree on this. So all of this activity is needed to describe how quickly the energy dissipates from excitation of electronic levels into thermal motion of
Slow
ions.
calm down.
Now, there is a big challenge for the solids.
Oh,
No, the complication is that, again, now, how many people have heard about K-points? What is a K-points? What are kind of K-points? I would say, how many people do not know what is a K-points and what K-points we are talking about?
I have a very vague idea. Like I couldn't like use them if I needed to right off the top of my head, but
Okay, but
I know what
just
to look for.
whatever your ideas, maybe you are really close to the truth.
Well, they're basically like they describe the symmetry of the system in some way. It kind of it tells it to basically like place other atoms in some specific position somehow based on like how many K points you have. I can't explain it very well.
Well, position of atoms is just the coordinates, x, y, z coordinates, right? Why we switching from space x, y, z space to the K points?
So someone else. Alisa?
I thought I knew, but now I'm very confused. I don't.
Well, say whatever your thought
What-
before. Don't worry.
What is the difference between K point and momentum?
I mean, I thought it was sending things in a direction. That's what my
Momentum,
general.
momentum, right?
Yeah, that's what I
Velocity.
thought it was. But
Okay.
Yeah?
and I thought I was just trying out different types of interactions between.
Why
like,
we don't use K points in the molecules? Like there are half of us, at least more than half, I hope, chemicists, right? And usually K point, this is a favorite jargon of physicists, but for molecules we usually don't use any K points. Any ideas why? Why momentum is not a good kind of, physical number, physical property in molecules,
Periodic.
but it's good for the solids.
And the question of momentum of what?
George curious.
Momentum of what? Of which of
Or the wave.
Oh,
Of
with
course,
whatever
ion-
you're sending at.
like ions, nuclei, they do have momentum when they have thermal motion. But here, these K points, we are speaking about momentum of electrons.
Yes.
Oh,
And not
okay.
individual electrons, but all electrons together as a big system. So all electrons
Block function.
translate in space
You already
simultaneously.
said the hint to my question. I guess it's now
function,
pretty
though,
obvious. My
is
initial
determined
question was,
by the K-
why are we not
like
using
the
K
brilliant
factors,
zone.
K points in
And
molecules
K
compared
point
to
different.
solids?
Simplified.
That's it, right?
The block
Anyone
is
wants to
periodicity of the
find
wave.
out?
Oh, I thought you were saying
The other
like
one, no.
block function.
Zero momentum.
Yeah, right? Because again, in your molecules, the orbitals, the electronic wave function is usually just localized on a few atoms. It really has no way to move anywhere, right? But in a big solids, your electrons move as a wave, almost as a free wave, right? All over the entire piece of your bulk solid material. And this is where, of course, electrons have momentum because they literally move all over, because the wave functions are really spread over the entire piece. It's completely hybridized, delocalized, right? And pretty much the same if you think about conjugated polymers. You start with a small single unit, whatever, PPV or whatever polymer you are thinking about, right? Then increase, increase, increase. So the larger the chain of the polymer you are looking on, right? So the orbital will be spread over the entire piece in this conjugated system, over all rings. And then when it's becoming really long polymer, it's becoming almost like a free electron, pretty much the same as in the solids. That's why conjugated polymers also called the conducting polymers. Right?
So she's using key points because everything's solid, or?
Well, now the trick is you of course don't need to use K points. You can just describe the position and symmetry just in this X, Y, Z space, in a regular space, right? But here is a trick. Because of the symmetry and because of this free motion of electrons, or almost free motion of electrons, and as Dmitry already said, collective, kind of, they all move as a wave all together with some kind of correlations in between each other. So you can think in, if you were taking Dmitry's class for both quantum mechanics, I think you touched it in the quantum mechanics mainly, right? For undergrad students, which you didn't, but Braden and London did, and you, well, maybe no. You were talking about wave packets, and you had a project on a wave packet in a K-space, X-space, right? So technically, you can always go from one coordinate to the K momentum space. And for solids, K momentum, the K point or momentum of electrons is really a good value where you can say, well, I can use just, like, because of the symmetry, you can use really just 2 atoms as a elementary unit cell for the solids, because then it's just duplicating itself, right? If it's having high symmetry. For example, the sodium chloride salt. So you can use just really very small unit cell in XYZ coordinate. But now if you calculate the electronic structure just with these 2 atoms and applying periodic boundary conditions, which you said you had a problem with, now I think you understand, like if you have a high symmetry, put in periodic boundary conditions, you kind of just having many replicas along wherever you're, if it's 3 dimensions and it's on all 3 dimensions, if it's 1-dimensional structure like she's having, then it's only on 1 dimension, and then you need a lot of vacuum to kind of make these replicas not interacting anymore. But the point is that now, wherever your dimensionality is, so you can thinking about that you can have really just 2 atoms and then duplicate it. But if you calculate the electronic structure, you will have not really very good agreement with experiment. However, if you include many K points in your calculations, which again can be based, you can calculate them based on the symmetry of the structure. So having just 2 atoms, periodic boundary conditions for the sodium chloride salt, and let's say 10 K points, maybe 6 K points would be good enough, then you will have electronic structures, the band structures, the density of states in a very good agreement with experiment. And another thing is computationally, to be in a K-space is much less expensive rather than to be in another way you can make huge unit cell, like not 2 atoms, but 22, I don't know, 200 atoms, right? And then just take a single K point, and again the result will be the same. So you either make your big unit cell to get good computational cell with many elementary cell, to have good electronic structure, to have accurate electronic structure. Or you can kind of think in that you will go to K-space, having many K points, and very small elementary unit cell with boundary conditions. Why is it more favorable to be in many K points? Because in the ground state calculations, you can parallel, each K point can be calculated separately, which you cannot do with XYZ coordinates, right? So now the trick is that you really can parallel, let's say you take in 100 K points, use 100 processes, and your XYZ calculation cell is very small, right? So of course you can do it very quickly. And then you combine all your information from each K point, making a dose or whatever, band structure, and getting good agreement with experiment. If you do backward, if you take a huge unit cell in an XYZ and calculating just 1 K point, you can parallel it as efficiently in 100 or how many processes, right? So of course it takes much longer time, because in this case the inclusion of many processes will be not as efficient as with K points. So that's why in solids people use this trick, thinking that you can always go to the K space, to the momentum, because your electrons really behave like a free wave with, of course, and again, wave is characterized by momentum, not like coordinates for wave is not so much important, right? And then you're saving a lot of computational efforts. However, in our case, this trick will be not working due to these couplings, because now in each K point you have to have a couplings between all electronic states, right? With indexes ij, plus between different K points, as many K points you are using. And now we really have to decide what to do. Either, but if you take a huge unit cell with many XYZ coordinates, right, many atoms in your computational cell, again, it's not really very helpful because again, it's very computationally expensive as well, right? So it looks like you really need to figure out how to treat K points kind of in a smart way, and for dynamics, it's becoming really challenging question.
So probably speaker didn't expect that we will stay so long on each slide, but before we went over the first line. What are couplings? So what are energy pop files for different K points? Can you explain to us?
It contains the number of states, like number of orbitals. We are interested.
You mean list of orbitals?
Yeah. So
Energies of orbitals.
Energy with your indexes I, right? Like for your, like each energy will correspond to your wave function psi I.
I is number of orbitals.
Index of
Index.
orbitals.
Yeah.
Index of your state,
Yeah.
which is also defined by your wave function psi I at that moment of time, right? So technically your energy pop will have all energies, I means going 1, 2, 3 or whatever, how many states you consider, also running through this T at each moment of time, right? So it's actually a massive array, right, of numbers for having indexes for each electronic level and indexes at each moment of time, right? Because with time you have energy of this level at initial moment of time, then next moment of time, next moment of time, next moment of time.
And you do have energy pop file for each K point separately, right?
Yeah.
On your previous slide, can you go to previous slide and show how to associate energy pop file with your band structure? Can you just show it by finger or by some tool on the image? Where are values of energy from your energy pop file on these diagrams?
So in energy pop files, it contains the this is band gap, this is HOMO, and upper one is NOMO. So here we can see just a couple of states.
But just let's say, choose your K point equals whatever. At this K point, your HOMA is whatever the energy of your HOMA.
Here.
Okay, and then LUMA obviously is somewhere there. Yeah, at the same K point, right?
Yeah.
And then if you take another K point, you clearly see that gap is different,
So here,
right?
if it is true, then here, this is the HOMO and this is the LUMO.
So were the different colors at different points in time?
No. Here it's not really dynamics, right? This is just
Statics.
static at some moment of time, let's say, right?
Okay.
Initial moment of time, and technically this is probably at 0 Kelvin, not heated yet, right?
No, not here.
It's just at 0 Kelvin. But each point on this curve corresponds to the different K point, right? That's why if you take in just K point equals whatever the number of this K point, you will have your HOMA-LUMA gap and energy for all other states equals to these values. But if you switch to a different K point, right, let's say on the other side of this graph, you will see that, of course, your HOMA-LUMA gap is now a different value,
Yeah,
and all energies also having a different value.
but what do the colors mean?
Oh, the colors correspond to different state. Like, magenta or whatever, red one is your HOMA at any
Got it.
different K point.
That's what I was missing.
Good. Good.
Because again, in a molecule where you have very localized orbitals, or in a quantum dots in a finite system, in other words, right? So you expect that your kind of energy will be just a straight line. It's not really showing any dependence on K, right?
Yeah.
Or very, very shallow, with very insignificant change due to the K points. However, in the solids,
Yeah, no.
you will see
I was
this
just
change.
missing that small part, but I got it now.
Okay, can I contribute and maybe repeat the same thing?
Okay.
So if we select k momentum equals 0, so we have energy of HOMO.
I
Here,
guess she can use just the pointer,
yeah,
right?
yeah. Energy of HOMO minus 1, energy of LUMO, energy of LUMO plus 1, right? And then if we select different value, let's say k equals 5.5, the dimensionless, then energy of HOMO will be here, HOMO minus 1 there, LUMO and LUMO plus 1 there. So it will be a list of all available energies at given value of momentum. And this list along this line, it is what Fatima is calling energy pop. So
At this, energy pop at this specific moment of time.
correct. Yes.
And it is
Technically, energy pop will have at other moments of time as well. So just
yes.
as one dimension from this array, right, in the energy pop.
And each energy pop file contains suppose 30 states below the HOMO and 30 or 40 states above the LUMO.
And at
Not
each,
all of the orbitals.
and also at each moment of time.
Okay, good.
Well, because it's dynamics, right? You go from
Yeah.
from your time equal to 0 initial state up to how many? 1,000 femtosecond. How long you make in your dynamics?
Yeah. So so for these 2 nanowares, for each nanoware we have 4 energy pop files, since we consider 4 K points, and for that one 3 energy pop files. So in order to calculate a rate field tensor, we need to consider, suppose for this one, we need to consider 4 energy pop files, all the coupling files, like direct and indirect. Direct means from K point 1 to K point 1. Suppose K point 1 is 0.1, so 0.1 to 0.1. Here 0.1 to 0.1. Suppose 0.2 to 0.2. So those are the direct couplings. And the folder, now we need to put indirect coupling also. Indirect couplings are suppose from 0.1 to 0.2 and 0.2 to 0.1, like all of this. 3 to 4, 4 to 2, all of them, like it should be 16.
Mm-hmm.
Wait, so
Yeah.
so this is the point of today, just so that we can ask questions? Okay, got it. Just making sure. I didn't want to be like ruining our presentation.
No.
No,
So-
this is more like learning
Like
kind of.
10 slides for 2 hours.
Okay. So then I have a question. Can you go back? Yeah. So if you're crossing, does that mean that like the solid is having 2 different K points at one time? If it's for the non-indirect, but not for the indirect? Or why would you even look at the different?
Well, technically, your solid, like now to have really electronic structure, you need to add together all energies at each K point.
File system on
And then your doors, like what you are drawing usually, you draw these doors at your single K
inside
point.
scratch
Now
001,
add
there's
each
scratch
K point,
001,
right? So
scratch
kind of
02,
it
scratch
becomes
02,
more denser. Your denser state
Yes.
becomes more denser due to the presentation. Some of them
Because we're
have to generate,
moving.
like for example, like when they're crossing,
If I wanna work in one,
it means at different K points.
Gaussian doesn't recognize something when I try to submit a job.
Well,
So that means you just shouldn't use it.
they're not crossing. It just means that at this specific K point, your whatever HOMA minus 10 having much lower energy, or like much closer to HOMA, comparing to HOMA minus 10 or whatever for the K equals 0, right? Like you have this different splitting, and when they come closer apart, it just kind of the splitting is different. But now you have to combine all them together to get your density of state. Right? And again, if you have enough K points, let's say you're drawing your density of state at K equal 0, just one single point, and you're getting your density of state with whatever peaks you have there, right? Then you're adding another next one, 0.1 or whatever.
No.
So, and now you see that you have additional peaks appearing in your density of state, and your gap becoming smaller. Of course, it's a significant change. Then you add in another K point. Now you see that your peaks just growing a little bit in intensity,
Temporary
but you don't have any new
change.
peaks. Then you add another K point, and you see that again your peak stays the same. You're just growing in intensity because you're getting more K points. But overall, your gap is not very much changing. Number of peaks, the shape of your dose is not really so much affected anymore. It means that 4 points is enough. You have now good kind of enough K points to really represent the real density of state for your system, right? Or maybe you don't see anything with 4, you're adding 5, and suddenly again new peak appearing, or your gap is decreasing. Means you probably need to increase your K points until you see that your dose is not sensitive anymore. So there are systems, typically in many solids, you have we call band gap those where you have the smallest energy between your home and luma along this curve, right? In your case, what would be your gap for your first right structure?
1.7.
But is it direct band gap for the which K point gives you? Like your gamma point is like your 0 K point, it gives you the smallest band gap in this case?
Yeah, this is direct band gap, first one. The second
So the first one is direct, but the second one?
Indirect.
Indirect. Means the smallest difference between your home and luma happens not at the same
Now
K
try
point,
it.
but K point, wherever your K points there.
So what's your batch
0
recipe?
and 0.2 or something.
Yeah, something like that. Like it's not a
Point, whatever, right? So this is also possible. And for example, many systems, like cat selenite is known as a direct band gap, or cat sulfide. Lead selenite, also known as a direct band gap, but not in a gamma point, but in another symmetry. So, but silicon is known as non-direct band gap semiconductor. And actually, this is one of the reasons why silicon is not very much luminescent structure, especially when it's in bulk materials. When you go to the quantum dots, then becoming luminescent. But silicon crystals not really luminescent crystals at all. And mainly because of this non-direct structure of their electronic structure, when again you really losing this to the phonons of different momentum rather than giving it to the just shining light through the photon. If this comes to understand.
Yeah.
Okay. And now on the next slide, there is a third line, correlation indirect.
Yeah, this is MATLAB code. I will describe in little bit details on the next slides.
So this is something really new due to these K points, right?
Yeah, so for we calculated a rate field tensor for all these K points.
Now let's make a vote. Who is hearing about Redfield tensor for the first time? Do not hesitate. Okay, who can go to the blackboard and derive what is Redfield tensor? No one. See, you need to give a little introduction. Very brief.
So
We don't.
again,
It's not.
we were just before. So we kind of more or less understand what is non-diabetic coupling, right? Then suddenly you're talking about Redfield tensor. How is it really connected to you? Like I can guess that you need.
Are they connected?
That they need a connection, right? You probably need to know your non-diabetic couplings to create your Redfield tensors. But what is this connection? And what exactly is the difference and why you need really these tensors?
Hi, Ben.
Oh,
Out of time, they
wait,
have
you
answered.
people, they can't hear you currently. That was Dimitri. This is Svetlana
It's
and
fine if
Dimitri.
you need to terminate on Los Alamos. We will share the recordings.
No, he did. He did not care.
He terminated us anyway.
Well, he was polite. He waved hand a couple of times. Now we can enjoy bigger image of John.
And you can talk, right? Because you can, we can hear you. Can we?
Probably not.
I'm not sure.
No.
No? Okay.
We need to project him on the bigger screen, and then system will share the sound mine as well.
So rate field tensor contains the coupling, like correlation between coupling files.
But why do we need it? Like, what is your goal? Why non-diabetic couplings not enough? So you got your non-diabetic couplings. They're already giving you some information about the interaction between electronic vibrational degrees of freedom and thermal
because we
motion of
wanna-
nuclear, right?
We want to study electron dynamics.
And in other words, you need kind of probabilities, no?
Probabilities, yeah.
Probabilities to go from one electronic state to another electronic state, right?
Yeah.
Couplings doesn't give you the probability, but they kind of connected to the probability.
Yeah.
And your tensors,
Yeah.
are they?
For transferring population from one state to another state, we want to see the probability of transferring from which state to
Okay.
one
So
state.
in other words, your Redfield tensor having a meaning of just probability of populating one state
these need to go
or
to
depopulating one
the
electronic state to
office.
another through
Do I have to do anything?
through the kind of
Alright,
using this energy
turn
to
it
the
off.
forums, to the vibrations of lattice. Oh, what is it?
It is the side view of Los Alamos conference room.
Ah,
Instead of switching, they just turned camera to the side.
oh, they were not able to disconnect us, I guess.
So this correlation, actually it's a correlation indirect, it contains direct and indirect both. So correlation indirect accord, it includes indirect and direct couplings both.
But again, your direct indirect means between the same key
Direct
points or
means,
different key points.
Direct means same key point, electron transfer from same key point, and indirect means one key point to another key point.
Everyone is happy, or everyone doesn't care? No questions.
They're still there.
Oh,
Braden's
okay.
still there.
Oh,
Oh, probably Ben just took Levi into different room
yeah.
because Ben needs Levi and doesn't need
Braden.
Braden at this point.
But Levi told me we have to go. I told them
That is the
both.
only reasonable explanation.
And let me make a brief disclaimer. So coupling files, there are a lot of them, and they're time dependent. And this Redfield tensors that are generated by third line correlation indirect, they are not time dependent anymore. They include average over time to make the procedure maybe a little less precise, but much more quick and efficient.
And this is again different with the surface hopping, right? Because in surface hopping, you're getting probability at each moment of time, not really, well, we kind of use again average over ensemble, but it's really still staying time dependent probabilities for losing, or you can say population is still time dependent. But in your case, population is still
Population
time
is time dependent, but transition coefficients are not.
Are not, okay. So
Which
probability
which
is kind
saves
of
like
just like a constant. Mhm.
so now you will be talking about the file. Sorry for intervening. So on the right side of your slide you
Now
have,
we're going completely to technical issues.
but they are critically important. Without them, next steps are not possible. Oh, see, you're so popular. He's taking screenshots. Janet. We will share recordings.
It's open, yeah.
So this triple R files with K-point indices are generated by third line of your previous slide, by this correlation indirect,
Yeah,
right?
yeah.
And now you are going to...
Second, R, this is second line. Energy
that's
hop?
the-
No, it is the third line. So
Oh, it's already this tensors.
it's partial Redfield tensors which have K-point indices written behind them. And now Fatima is going to tell her major
What's it called? R.
It's just a name.
Doesn't have any special meaning?
Red pig cancer thing. Starts with R.
about John may remember it. About 4 years ago, at our group in South Dakota, there was a couple Wendy and Adam, and they gave their version why the files are named RRR. When they presented it on the group meeting, they brought a cartoon of a pirate, like written by hand, on like a crutch with a sword, and telling, "I'm so angry." Okay, just historically. So Fatima is going to tell how to combine these many partial RRR files in one big file with 5-fold R.
Here we can see RR file. This one is K point. So this is K point 1 to K point 1. This red field transfer for K point 1 to K point 1. That means it is for direct transition. So same K point. This one for indirect transition, K point 1 to K point 2. So these are the K points. This is
Oh, but before you go there, I think
yeah. Now
we kind of, I would say, we have a code which is calculating all these RRR
yeah,
couplings,
I'm going to tell you.
right? And for code, of course, it doesn't matter whether it calculates couplings between the same K points or different K points, right? Wherever your input files, it will calculate. So more or less, it's clear how, like generally, without technical details. So we understand how you got your RRR files. But what exactly is the goal now? Like why you need these 5 Rs there? Like you're already happy, right? We have all these couplings. Why to combine them? Why to care?
Great question. We are looking forward for a great answer.
So it is like a. So I think it is complicated to deal with this all of these 16 files for electron dynamics because we need to study the electrodynamics in the silicon nanowire. So if we can.
So you're trying to combine 16 files into one file.
Yeah.
And you're saying this would be simpler. I mean, for simplification, like I kind of don't, I cannot just believe right now that combining 16 files into one file is somehow better than just small 16 files. Super.
It is a big file, like the indices are big, but and for further step we can just proceed with this one, like for electron dynamics.
Enough? Or should I help?
Maybe there are some other ideas. I don't know. Maybe Javid.
Javid, are you
looks he knows
asking
much.
next question, or you are giving answer to this?
No,
one?
it's not a question. I'm just clarifying that the RRR is the state 1, state 2, and the K.1 and K.2. That's the dimension, right?
Okay.
They have all transitions.
No, I mean, what is the
Between all
full
states.
Wait. Your question is technical.
Okay, I
Let me answer the question from.
There's not a question, just I'm clarifying that is the
a
RRR.
clarifying question.
I mean, I'm clarifying myself is like, is a transition 1, band 1 to band 2, and K.1 to K.2. Is that 4 parameters there?
Yes.
Okay.
No, it's
No,
you
no,
have
no.
all information for all transitions, not just one transition.
Just whether it is 4 parameters process, yes.
Yeah, okay.
Let me. Would you like to answer?
There are only 2.
I wanted to say something.
Okay, please.
So
please.
this one is transition probability from one K point to another K point, 1 to 1, and this one is 1 to 2. Yeah, so we want to produce this one because the transition probability between this one to that one and all of them. We want to feed all of them to
Sufficient
Why
or not?
transition probability.
I understand what she's putting them together. I still don't understand the reason why we need to
Okay.
put them in one file. What exactly is the goal?
I'll go to the camera and we'll make a hand-waving argument. So, the goal is to explore the coupled dynamics, where we can take into account simultaneous transitions of electronic population between different bands and different K points. We do not want to follow 16 threads and send information between them. We want to make it as a one unit, or one dynamics, which includes momentum as degree of freedom. So it is goal of convenience. On another hand, from programming point of view, we already have a subroutine, a unit that takes the matrix of transitions, energies, and initial condition for occupations, and then solves for dynamics no matter what is in this matrix.
Oh, okay. So you just don't want to change the format of your codes.
Of the
So
subroutine,
instead of taking this input information on your couplings from 16 files, you just combine it together because your code is dealing just with a single file. So-
It's a huge advantage there. In case of Python, I don't know what's the MATLAB, the opening and closing file is take a long
Plus,
time.
you don't want to deal with
Yeah.
16 files just from computational point of view. It's much easier to open one file with a lot of data rather than 16 files with small number of data.
If we go into 16 files, need to open 16 times 16 times
Really?
16 times 16.
And then close it.
Right? Yeah, and close it. So it takes too long time. Yeah.
Okay, but this is more like just computational problem. It's not really dealing with any methodology approach.
No, it's
just
purely
computational
computational
algorithmic kind of
algorithm.
approach.
Algorithm.
But it will if solved, it saves a lot of time.
Time, yeah.
So it's a question of computational efficiency.
But am I right? For your files RRR 11 and so on, right? You can really calculate each of them completely independent, right? So in other words, let's say you have 16 processors or whatever, 16 nodes, each
Yeah, that's what-
calculating each of them separately. So after how many time it takes you to get just one file, right? You kind of parallel it on 60 nodes and getting it at the same time as you would get one with a one node calculation, right? Okay.
So in our previous study, we calculated them separately, like for our file for 1 nanoware. So here, we combined 16 files. Now you go to the next slide.
Oh,
This is the
just
best
check
work.
if everyone understands and then.
This is the first we calculated a red field tensor for direct transition, meaning transition at the same K point, and then those red field tensors are feed into a super index tensor here. Then we calculated indirect transition, red field tensor for indirect transition, and those also went to all of them in this 4 index matrix.
What is the difference of the first RRR and the next RRR? The first one is isn't it should be I, J, K,
This
K,
one,
or
this one, or this one. It
Yeah.
has 4 indices.
so the first in this?
We introduced here another 2 indices. Here.
Well, for
Because-
direct
in the
ones,
first
you, have,
one,
you don't need 4 indexes for direct ones, right?
No, I mean in the first one, RRR is defined as what is the first indices in that one?
For this one,
Yeah.
I didn't put them here. There are a couple other lines also.
But in that one, the first one is I, the next one is J, and next K.1, K.2 is a K1 and K2 maybe, right?
Mm-hmm.
But now it changes to I, K, J, K. Isn't it should be I, J, K, K? What is the...
It's just convention how she likes to order indices. Just it's important to keep the same convention in all subroutines. You can agree between yourself and your program. You list 2 electronic indices and then 2 momentum indices, or 1 electronic, 1 momentum, and then second electronic, second momentum. Right?
But how is in the matrix defined that in that case? Isn't it change the dimension then in that case? If we, isn't it same matrix the first RRR and the second RRR?
So Javid wants more comments. What's the difference between triple R and quartic R?
No, actually, no. They have
No?
a 2 RRR in the 4 RRR.
Yes.
Sorry,
This one,
first RRR on the first green line. Yeah, that RRR, and they have another one on the in that one. Yeah.
So
You're saying
is
that
that,
the
is that the
measurements
same
don't
matrix?
line up, right?
Yeah. So,
Yeah. Because I'm wondering the same thing right now.
Yeah. So isn't it is that same matrix that we have? If the same matrix, the dimension is the name of the
Okay.
fund.
Javid is identifying inconsistency in notation of the 4 times R in the upper part of the code and
Can
4
not
times
be.
R in the lower part of the code. You are correct. There is an inconsistency.
Is it a mistake?
But whatever, if it is formally yes, but whatever is written last overrides previous one. No, K.1, K.2 are different. But I don't know why this top line is needed. We can live without it, right?
John knows the answer.
John knows. John, do you know?
But
But
we
we
can
need to
hear
put
him,
him on
right?
a. We need to put him on the screen so we can.
Okay,
If
if I
you get pain to switch between, you can do it, but only once.
You have one shot, John.
John?
No, it's not John. It's Brady.
Okay.
Yeah.
easier.
Okay, but you can hear me. So to just kind of clarify what Dimitri had said about later in the code, it overrides what was previously stated. So that very first line, the 4 RRs, and then distinguishing K.1 and K.2, this isn't necessarily because then once you go further down, like these so K.1 is the same thing as this little k, and the K.2 is the same thing as large K. So when you're looking at those 2 lines.
Yeah, but matrix dimension will be changed different in that case, right? In the first one and second one. If we
Yeah, they would be
calculate
shaped differently.
Yeah, shaped differently.
Yeah.
Satisfied?
Yeah, it's made shape difference, but I don't get it why is shape changes in the middle of the code and the same matrix then.
It is not a final product yet. It is development version.
Okay.
More questions to John?
When-
Or any comments, frivolous?
maybe later on,
volunteer,
John, are you coming on Friday? You probably send me email. I just by some reasons my Wi-Fi doesn't work.
Oh,
Are you coming this
I
Friday?
did send. Well, I did send you an email, and read it, and then we will discuss.
We will
So
probably not-
I'm planning on it, but I forgot that we already had a trip planned for this weekend, and so either what I'll do is we'll leave Thursday night, and then when I get
Okay,
to where I'm
can you
going,
come
I'll
next
drive up to
Tuesday?
Fargo.
Okay, I make you
Yes, that
choice
was-
easy. Next Tuesday will work better? Okay, then
Yes,
plan it
that-
for next Tuesday then.
Okay, perfect.
Okay.
That's what the email says, but that's
we
what I'll
need-
plan on
we
then.
need you to sign the agreement for the how's it called? Virtual something, right?
Some paperwork.
Okay.
So if you can sign it and then email it to me, the copy, as soon as possible, this would be helpful.
Okay.
If not,
I will take
then
care
we
of
will
that.
do it on Tuesday, next Tuesday.
Okay.
Good?
Okay, so let's turn back to scientific part, and after the end, if you have time, we will return back to administrative.
Oh, we're done, at least with John.
Okay, John, you will be cut from audio
From
line.
voice.
Okay, let's continue.
So finally we have this supermatrix here. Now we
So what is the goal for this piece of code?
Where's escape? or do you discard?
Probably hit the X, because I think that's trying to quit then.
Okay, so the next slide, we make this a 4-index tensor to
Something is missing?
So we make this 4-index tensor to 2-index tensor here. Previously we had R, I, K, J, K. Now we have I, J. So here defined here. So we consider if we write code this way, same K points will be considered first. And after the if you run this code, we will get energy pop file also. This energy pop file will combine all of the all energy pop files for different K points. So if we run this code, then that correlation indirect MATLAB code, finally we will get these two files. And the combined energy pop file, and this is Redfield tensor.
So, Fatima, can you remind us why we need these files with complicated abbreviations? Just repeat, we were already discussing it.
Which files? Like
This,
Just again, what's the goal here for
this
this
piece
slide?
of code helps to generate this 5-fold R and 5-fold E. Why this 5-fold R is needed? Why do you need to convert from 4 indices to 2 indices?
to make calculation simpler.
Okay, to use older subroutines.
Yeah.
And what is the difference of these 2 indices, 2 super indices, compared to old 4 indices?
So these 2 super indices covers the 4, includes the previously 4 indices using these 2 lines.
Okay. And how do you build these super indices? What do they mean? How this index run? Your circled part. Can you explain with more details what it is?
Yeah. So this K is K point, number of K point here. This K makes like
Index,
4
okay.
K points. This big K is also 4 K points because now it will go 1 K point to another K point. So we are consider 2 lines, 2 loops here, and this number of states, number of active windows, like in energy profile we have a certain number of states. So maximum number of states minus minimum number of states plus 1. This is the n states. And I is 1 through number of states. If it is 70, then 1 through 70. And J is also 1 through 70 number of states. So we have 4 indices, and we, just to simplify, we include this big I, and we include small k and I into this big I, and this big K and J into this big J. Now it's simpler.
Okay, can you go to the slide number 3 with band structure? Okay, and can you point where are different values of these indices on this diagram?
Big I and big J.
Let me do it, okay?
No, I'm just asking the question of is it
Let
capitalized?
me do it first, then you ask questions. So this big super index will list all energies in this band diagram. So it will be 1, 2, 3, 5, 4, until 70 number of states. Then it goes from here. and go 71, 72, 73, list all energies for the all bands in the next key point. Then it will roll over and start all bands again in the next key point. So it will list all energies included into the band diagram in a linear fashion. Yes? Okay. Please continue.
And these are the image for
So those are
three
examples.
different nanowires. So it's not like what we did before, like HOMO and LOMO. It covers a range of states.
Mm-hmm.
So here it covers 0 to 100 steps for I and J. Like it is, suppose it is 200 by 200 matrix. I covered in this image only 100 here, and in this image 1 through 120, and this one is 0 to 160.
So for visualization purposes, you are showing not the whole five-fold R matrix, but small fragment.
Yeah, part of it,
Okay.
not all of the states.
But in that case, is it missing some K point then?
It is only visualization.
Okay.
So she has the complete information, but it's already too many details compared to what human can understand.
Yeah, for calculation we consider all, but here in image we just consider per number of steps. And for dynamics calculation, we need this RRR file and combined energy pop file. So this is the form of energy pop files. The combined energy pop file for all K points. And we need this MATLAB code process, dynamics.
So you funnel these two files at the top to the code at the bottom.
To use in this MATLAB code. I found this code from the previous MATLAB code.
Okay.
So there are many approximation like
Now,
initial state coupling is continue to the dynamic whole time.
To my understanding, right now there is a debugging procedure for merging these two pieces of codes together.
and if we use these two files in this code, and if we run, we got this error. I got this error, this message. So something wrong with the matrix dimension. I need to fix. John already has some suggestions for me. I will implement those.
Okay, so probably right now it tells that your dimensions use variables based on single K point, like this variables HOMO, orbital minimum, orbital maximum.
Yeah.
They are for single K point.
Yeah.
And for this five-fold R, each of these numbers needs to be multiplied by number of K points, by 4, yes, and then it may work right away.
Do you know what's happening in your code on line 310? You're getting the error in line 310 in your MATLAB code. Do you know it's
yeah.
exactly
Right
what
next
you're
line
trying
it shows.
Oh, it's the next one there. Okay.
So I need to modify this line, this energy of electron, and this one.
So E is a scalar number or is it a matrix?
No, E is
Based on the error message,
Oh, okay,
it looks like it already
It's a matrix.
went through part of the dynamics and it stops at point of computing observables.
What is the O max, O min?
the number maximum states in the energy pop file, maximum number of states I consider. the highest number of state actually.
So sometimes electronic structure codes compute like 1,000 of orbitals in the UV or X-ray range, and we do not need them. We need only optical range in the vicinity of the gas.
So seems like dimension of energy pop supposed to be equal to the dimension of other one. E.
Yeah, dimensions on this side and that side should be same. Right now they are not same. So,
Okay, maybe next time you present, you'll show how this bugs were fixed. Anything else?
no, this is the last slide.
Do you want to give credit to John and Yvonne?
Yeah, yeah.
Just tell it.
John wrote the code actually, and Dr. Killian had fruitful suggestions, and Yulon. I saw Yulon a couple of times.
Okay, let's thank Fatima. Any questions in Fargo?
Have any reference on the similar calculations or anything like that?
Huh?
Do you have any reference on similar work like these things?
Yes, Keiichi Yamashita in Japan.
I want to take a look on that.
Yep.
Keiichi Yamashita.
Yamashita, first letter of name K, first letter of the family name Y. Any questions in Los Alamos or in South Dakota?
You can speak. We can hear you.
We should be able to.
No, probably we don't.
Oh, we got.
There we go.
So I mean, I've got a couple questions, but we can discuss them next week more in
But,
terms of.
Please give us, or please give to Fatima a heads up what she should start thinking of.
For next week.
Well, so one of the things that I've had a little bit. So in terms of taking this huge red field matrix that contains all of our transition probability, putting it into dynamics and pulling out the different points. So is it something that because it's the one large matrix, it's just going to automatically know to cycle into the next K point as it's going through because of double indices? Does that question make sense?
Okay, we will think about this question until next week.
Okay.
I missed the question.
John, please type it directly to Fatima because audio connection is not perfect.
Okay.
We just got general direction of me. Braden, do you have any questions to the speaker? Okay, then let's thank Fatima once again. So, if you are wishing to contribute to next week's presentation of a little bit more simple discussion on electronic dynamics for single K point, you can access this file in Google Docs and write your name. If you don't, it's fine. Then you could be assigned. What else? There will be schedule for Friday meetings composed by Professor Killian with mostly focus on journal club.
And this Friday, Jabin is given the journal club presentation.
And in case you were making some notes and critical comments to the speaker on her printout, you can return it to her for future improvements of the code and presentation.
I'm supposed to go next Friday, but I won't be here. Does somebody else want to?
Yeah, we should use probably Ben. Maybe we will have to substitute for Lisa.
I'll try.
It's still enough, how many? Yeah, the whole week to prepare, to read the paper and present. And also, I didn't put Braden. Braden, can you hear me? Yes? So I didn't put Braden on a journal club presentation, just thinking that you're probably busy with whatever stuff you're doing there, but I put you on a research presentation, right? Sometime in July time, right? But if you really have a very strong wish to present the journal club or whatever the paper you think is really you want to present, let me know. We will squeeze you to the schedule. Yeah, it was yes if he will wish.
He thinks that we can't hear him.
You done?
Mm-hmm.
Anyone wants to discuss anything else? Okay, many thanks for your enthusiastic investment in this intellectual feast.
But who is giving presentation next Tuesday?
It will be several speakers.
It's intrigue.
It is yes, it is intrigue. Okay, meeting is dismissed.
Be down.
So I can't meet you on Friday, and since I'm gonna be gone all of next week, use this schedule. So I'm missing this day because I won't be here.